Thank you. Yeah, so I'll be talking about what I've called the state of the art in Amiga 4K intro programming, and more precisely, I'll simply be presenting my my special 4K intro system that I've made for making 4K intros. There are some varied ideas in that that might be interesting. So it's sort of a bit of presenting various tricks and various pieces of code and that kind of thing. So let's first sort of recap what's special about coding on Amiga. So we know that there's no graphics API, no powerful graphics hardware, no libraries you can link to that can do all sorts of things for you like there's in Windows. There's just the CPU and the hardware, and that's it. So you have to, well, you can use the system to set up screen, but then you don't have so much control over it. So usually you don't just do everything by banging the hardware, and especially things like rendering when you're transforming points or transforming whatever you do, rendering all the polygon renders, that kind of thing. You don't get that for free. You have to write it all yourself. So it's all the software rendering, and you don't even have a chunky buffer to write into because the Amiga uses planar buffers. So you have to have a chunky to planar conversion routine, which can also be quite big. So all of these things have to sort of fit into the 4K. So there's a lot of things to do before you can actually start making the effects. You also have to do the sound from scratch, but that is actually quite easy. It's just to say, play this sound with this frequency, and then it plays it. So the hardware is quite simple in that sense. So a bit of general things about making 4K intros. So the first thing might seem a bit weird. Why am I saying you should not optimize for size? Well, the point is you should optimize for the compressed size, and that might be a completely different thing, because you can have some code which you repeat, and then the compressor which you run on your program afterwards will compress the stuff away. So you could easily run into situations where the uncompressed size is bigger, but the compressed size is smaller. So you should always aim for the compressed size to be as small as possible. But the problem here is that you can't just optimize for size and forget about the speed, because then your thing will just be horribly slow, because it's still a slow machine we're doing this on. So you have to sort of strike a balance between optimizing for size and optimizing for speed. And then there's this way of going into making things that I have found useful is this sort of three-step thing: generalize, parameterize, specialize, which means that first you make some very general routines, some very general effects. You figure out you need something to do transformation. You make some very general transformation code. You make some very general effect, and you try to parameterize it as lot as you can. So every time you can do something in one way or another, put in a parameter to do it like that. Because when you have all these parameterizations, then the chance is bigger than that when you are putting together the 4K, you can use this routine for many different effects, which is where you actually get something from the 4K. Then when you're sort of ready, you know what should be in there, and maybe the size is a bit too big or whatever. Then you can see, okay, so what parameters are not used, what features of all the general code are not used, and then remove it again. And so don't try to think specialized from the beginning. It's the result I find is usually better if you take this three-step strategy. There's this thing about one effect and using it in many ways, as I just mentioned. Siko of Scarab has had this term that he called this a master routine. So you have a master routine that can basically do all this stuff, and then you just parameterize it to get different results. And that's generally what you should aim for in a 4K. And you shouldn't think, I want to make something that looks exactly like this, and then try to make that as small as possible. Try different things and experiment, and if it looks good, that's great, because then you will get much better results than trying to achieve something specific. So that's sort of the general experiences of making 4Ks. So the question is then, what language should you use? So I think actually nobody uses C or C++ for 4Ks on Amiga, because you have to do so much size optimization, and C and C++ is not good for that, because so you know there's this 10-19 rule that says that 10% of the code is responsible for 90% of the execution time. And that's just not true for size. It's not true that 10% of the code is responsible for 90% of the space, obviously. So you have to size optimize everything. So it's always better to write the thing in assembler. But what's even better is to invent your own language to write this thing in, because even assembler might be inefficient. There might be some instructions that do not compress very well, or quite big, or also there's, if you specialize your language to exactly what it is you need, then you could end up being able to compress it even more. So that's mainly what I'll be talking about. So when you want to design such a language, then that you could make a couple of observations about Amiga code in specific. So FPU instructions are very big. So all of these floating point instructions are at least 4 bytes long. So when you make FPU code, your code just blows up and becomes huge. So we want to get around that somehow, because we want to use floating point calculations, because it's much easier. And most of the time, when we're doing integer calculations, we are making it just using 32 bits all the time. But all the instructions have possibilities of also being in a 16-bit and 8-bit variants. But we don't actually use this possibility, so there's sort of wasted instruction space if we only use 32-bit anyway. And the same thing with the offsets from when you offset from an address register. You don't use all the 16 bits of the offset. There's typically only a few different values you actually use, so you waste something there again. And when you write your routine, so the Amiga has quite a lot of registers, at least compared to the x86 processors. So there are usually many ways you could swap these registers around. You could swap 2 registers and it will do the same thing. And that means there's some kind of redundancy in the representation. And when there's redundancy, it usually means there's some opportunity for optimization, or some opportunity for representing it in a smaller way. So that also could be nice if our representation could take use of this somehow. So in general, there will be patterns in the code that the compressor will not be able to see. So you should somehow take advantage of these patterns yourself to make the size smaller. So what do we actually want from such a language? Well, first of all, we want it to be compact. We want the case to be that if we write things in this new language compared to normal assembly code, then the result is smaller. And we also want it to be useful, meaning that we want this language to actually be able to express all the programs, all the effects that we want to write. And by convenient, I mean that it should also be easy to write in the language. You shouldn't have to write all sorts of weird codes in your assembler, and which you can't see what actually is, and so I mean there can be many ways that you can actually structure this process of writing in your own language, and it's a quite important design goal for this to be convenient, so you can actually write in this. And then it should be possible to take your own representation and then translate it into the normal representation in some very compact way, some very compact routine that can do that. So these are the things we want. So how can we achieve this more concretely? So actually, design decisions, the things I decided to do. There was sort of two approaches one could make. We could make a completely new set of instructions. Just invent a couple of new instructions that we thought these would be useful to have. Or we could just go with a subset of the original instructions. Say we take the original instructions, but only use some of them. And I've taken the second approach, and that's mainly for performance reasons. Because if you have some other instruction set and are translating that into the normal instructions, especially if it's a very simple translator that you have space for in the 4K, then the result will be a very slow code, and that's probably fine if you're doing it for PC, but it's not just good enough for Amiga. It has to be. You have to be able to write fast code in it as well, and you don't have space for any kind of optimizer in your translator. So that's why I chose to just make it a subset of the instructions and translate into those same instructions. And then you could also choose between, should you just interpret the instructions as they come along, or should we translate the whole bunch into the real instructions and then run that? And again, for performance reasons, we of course compile it into the real instructions and run that afterwards. So I've chosen the kind of RISC style thing that either you do operations on registers or you load or store from memory, because that reduces the instruction set quite a lot. So you have many fewer instructions to have then, and much of the code you write you can write just as easily using this kind of style, and so in the end it would actually get smaller by restructuring it this way. Then all sizes are 32 bits, so it's only for integer it's only long word sizes. For floating point it's only single precision, and when we have offsets they're always divisible by 4. And index factors, when you have an index register and multiply it by something, you always multiply it by 4. All these things that are the things you need when you only work on 32-bit values. So you don't need all the other things the instruction set can do. So that also reduces the instruction set. We want to have very compact floating point operations. That means we need to use a larger part of the instruction space for floating point operations. So that's also something we do. And then there's this special thing, an escape mechanism. So we can decide this subset of instructions that we can represent, but often you get to some situations where it would be nice to just have this instruction or this instruction that you didn't include in your set. So you have I have some escape mechanism where you can say, oh, so now I escape and have real instructions for a couple of instructions, and then go back and have the compact ones again, and because then it gives complete flexibility. You can use any instructions, and then as long as you just stay with your own ones, it will get compact. So that's sort of the design choices here. So just like a 4K has this master routine, then the 4K seminar should have a master slide. So it's this one. So this is the whole instruction set, and I hope it's not too small. I hope you can see it. Okay, so I'll sort of walk it through quickly. So you need to have some kind of integer operation. So here on the left-hand side is the encoded when the instruction format are used internally. So there's the instruction here where the letters correspond to the fields out here. And then there's the decoded form. So this is how the instruction is normally represented. So you can see it that all of these instructions are usually quite a lot bigger in the normal format than in the compressed format. So you have to have sort of basic integer operations, and I'm mainly just moving some bits around here. And there's a special thing here. You can see there's only 6 of these operation bits here, but there are 7 here. And the reason is that these 4 bits here only have only 8 different values. So this captures actually all of the basic integer operations: move and add and subtract and multiply and all basic stuff. So it's very easy to. I mean, that's sort of the general strategy, not to have individual instructions, but sort of to have the general patterns where just move around the bits, and then you can have a lot of instructions just in one kind of instruction. Then there's a data transfer to and from memory, so you can move from an offset from an address register, or with an index. Here again, there's the ×4 scale, because that's the only thing you need with a 32-bit addressing. So these are basically the only addressing modes you need. So you can load into data or address registers, and you can store from data and address registers. And that captures mostly what you want to do with reading and writing from memory. There's a load effective address also. Where is the pointer? Oh, there it is. So, and a conditional branch. Normally, when you have the short form of the conditional branch, you have 8 bits for the branch offsets, which means you can branch up to 128 bytes in each direction. But the lowest bit of this one is always 0, because this instruction is always at even offsets. So in this case here, in this spatial instruction, there's also only 8 bits for the offset, but I just shifted up 1 here, so we can jump twice as far in the same address space actually, and that is actually makes quite a big difference, because it's quite often you have these loops that are larger than 124, but not larger than 256. So that saves a bit of space there. And the branch. So this is the call instruction that is different again, because it translates these normal relative offsets into absolute offsets, and that gives quite a big bonus, because then when you call the same function from different places, the opcode will be the same. The instruction will have the same bit pattern for all the places, instead of normally when you're calling relatively, it will have different bit patterns. So it compresses better if you change it to absolute addressing, and it's absolute compared to the start of the code. So, and there's also the loop instruction, decreased loop instructions, which are normally 4 bytes, but which is reduced to 2 bytes here again with this 12. So of course it's a bit fewer bits for the offsets, but again this is usually sufficient. And then you see all of these floating point operations. So normally you see all of the floating point operations start with 4 ones, and that's sort of the corner of the instruction set that's normally the instruction space that's normally used for floating point operations. But I use much more here, because you need to sort of read and write floating point operations, floating point values, do operations on them, and so on, convert to and from floating point and integer. So this way you can put all of these floating point operations, and actually you see these dots here means that these instructions are actually larger hubs. They're actually 6 bytes, but all of these get much smaller this way. So the special thing is where is the pointer again? There it is. This one. So usually in your 4K you have some block of data somewhere, and you want to get pointers to your data. But if you each time you want a pointer to your data, if you need to store the whole 32 bits of the pointer, or maybe a 16-bit offset into your data. But usually most of your data is some fairly small areas. So like here it's if it's within the first, or actually it's within the last 512 bytes of the data, it's only a 16-bit instruction, because it's then it's just encoded in that. And it's sort of finding these various instructions that occur frequently and trying to give shorter codes to them. So that's sort of the basic idea about all these things. And you can see the last one is this escape mechanism. You just say that now there comes a number of instructions that should just be copied directly. And now there's this special thing, that the second last one, which is the delta repetitions, or the multiplicity as I call it. So let's take a look at this piece of code. So this is just a snip from some matrix transformation code, 3D transformation code. And what you see here is you read some different offsets from, and that's reads from the matrix into some floating point registers, multiplies it by the point and adds them together, and that's the result of this row of the matrix operation. And there's the observation here that here you have 4 instructions in a row which are the same, except they have different offsets and different registers. It's the same with these 3 instructions, and it's the same with these 3 instructions. So if you had a special way of encoding these, then it could get much smaller. So what I do is that there are different things in the instruction that can, where it could be relevant to sort of increase it by 1 each time. That could be the register numbers, it could be the offsets, could be index registers, that kind of thing. There's this special multiplicity instruction that means now comes a number of instructions which are the same, just where these things are either the same or increasing by 1 each time. And this is where we take advantage of this register redundancy I talked about. So there's redundancy in how you place the registers. And now you reduce this redundancy because now it matters how you place the registers. You can order the registers around so that they have a specific order, and then you can compress that in a specific way. So if we scroll back to this list here, you can see that down in the delta repetition instruction, there are 4 bits there called X, Z, I, and Y. And if you look at the similar fields in the rest of the instructions, there are some X and there are some Z and I and Y. And you can see that the beginning of those are exactly 3 bits spaced apart, each of them. So it's a very simple way of taking this mask, just blowing it up, and then just adding in each time. So there's a very, the implementation of this multiplicity feature is very simple, and it's very, very good, because the first time I did it, even before I had optimized my code for it, it just saved 100 bytes in the compressed size of the 4K, and you can write your code so that it even gets better. So that's even another feature that makes it even less. And even when you only have 2 instructions that have a pattern like this, it is also better, even though the uncompressed size is the same, because you still have the instruction and the multiplicity instruction. But the fact that you have so many multiplicity instructions throughout your code means that these multiplicity instructions pack quite well. So just replacing 2 instructions by a multiplicity instruction and the other one makes it pack better. So that's about the instruction set. So now let's look at some code. Oops. So the demo system I made is not just this instruction set, there are also other kinds of macros for doing these things efficiently and for allocating memory efficiently and compactly and so on. So I'll try to show you some of these things just for inspiration. So let's look at the Ikanim source code. So let's sort of start from the beginning. So just ignore this thing here. So what you see here is it includes the system, and then there's this macro called begin 4K, and it has a file name and a number. So what does that mean? Well, it's the point here is that I can assemble these in 3 different modes. So when I write 0 here, it means this is the test mode. It's just assembles all the code and does nothing special about it. So I just write the instructions. It forgets about all the special instruction encodings and that kind of thing. It just assembles it, and then I can run it, and that's sort of for testing effects and so on. So I can try that. Yeah, so that's Ikanim. And then there's a different. If I write, instead of having the 0 there, I write the 1 there. Oops. I know I should have used some describingly named constants for this, but it's so much easier to just write the numbers. So what happens when I run it now is, apparently it doesn't do anything. But what it does is actually it assembles the code as normally. But when I run it, instead of running the code, it transforms the code into the compact format and writes it to disk to this file. And it also takes all the data that's included and writes that into the data file on disk. And to actually use that for anything, I can use number 2 here, and as one is a bit weird. So this one doesn't run because what it does now is it includes the data files that were generated before, but then it ignores everything in the actual source code, except that the actual intro system is now in a state where it is meant to be written to an object file or to an executable file and compressed using my cruncher, and then it will run. And then now it's a sort of compact format. It only includes the compact instructions, and then has a small piece of code for decompressing it. So it's very easy to develop things by having this sort of 3-step process and having conditions and that kind of thing in the code for and macros for doing that kind of thing. So I find that a useful way of doing this. So there's some. I've tried to make the system modular in the sense that normally when you're writing sort of very specialized code, very complex code, you write it all in one piece because then it's easier to see how the things depend on each other. And if you have some data, you want all the data to be together, so you write it together and so on. But often you have different parts of your intro, and you want each part to sort of declare its own data and declare its own memory and that kind of thing. Just want it all to compile together. So if we take one effect here, let's take the tunnel, for instance. No. Yeah, bad example again. So let's take the 3D engine. So now there's a couple of macros here. It says var and it says fast field and so on, and these are actually allocating memory. So what this means is, so there's a sort of memory allocation system where instead of just having blocks of memory that you refer to by a pointer, because then you have to sort of have this pointer in the instruction each time you refer to it. Instead, there's this structure that is always pointed to by the same register. So A4 always points to this base structure. And what this does mean, what var means, that means allocate one place in the base structure that I can use as a variable. And then that's what it does. And the fast wheel means allocate a piece of memory of this size and put a pointer to it in the base structure. Then you can just fetch the pointer by an offset from A4 each time. So then it get all of this handling of getting hold of the memory you are allocated gets smaller this way because you have it all in one structure. And the sizes of these pieces of memory then are encoded in just a number of 16-bit numbers, one after each other in a special structure which is made when this is compiled, so that so when this is all that this results in sort of in size of the resulting intro is just these 16-bit numbers indicating the size of the pieces of memory, and then this structure is run through, and the memories, the pointers are put into the base structure, and then they're there to be used, and that saves a lot of space by allocating memory this way. Let's see. Okay, so there are a couple of things, couple of of concrete tricks for saving space and so on that I will also show to you. So one is for setting up the screen, because normally when you're setting up the screen on Amiga, you have a cover list, and you give the pointer to the hardware saying, here is how to initialize the display registers to set up the screen, and that's fine. But the problem is that this structure takes up space, of course. But as you see here, so these are some macros. But as you see here, then the numbers that we actually put in here usually just increase by 2 each time. Many of the times just increase by 2. So we could perhaps place this structure in a bit more efficient way. But then the hardware would not be able to read it because it requires this in this form. So what we do instead is we just put it in manually. And where's that? And there's a very small routine for actually doing that. So actually, I don't use a cover list at all. It's just putting the things manually into the hardware in a vertical blank interrupt. So yet another space saver. Because when we look at the data up here, what the macro does here is actually it just saves the difference between the two values, -2. So many of these would just be zeros, and then it will compress much better. So I think I'll swap back to the slides, because there's something to say about sound, about music. So you could the most common way of playing music on Amiga is just to, each time you want to play some sampled sound, you just say play this with this frequency, and then you stop it and play the next sound where the next instrument is turned on. And the advantage of this is that it doesn't take any CPU time, basically. It's just you have all your samples pre-calculated, then you start them at the right times. But if you want to make really nice music, then these 4 channels that you have for playing these kind of sounds is just not enough. If you want to make echo effects and maybe many channels and so on. So you want to make sort of music that's of the quality that you normally see in 4K intros these days. Then you want to use some kind of mixing. You want to mix it all into one audio stream and replay that back. So usually when you do that, you need some kind of audio interrupt. But setting up such an interrupt actually takes up quite a lot of space. So what you can do instead is you can just use the knowledge about this is a special thing about Amiga that the display and the sound hardware and all these things are actually using the same timer. So you know when you're running in a PAL mode as all Amiga demos basically do, that there's this audio clock that you use to indicate the sampling frequency of the data you play, and you know there's exactly 71,051 audio clocks in one PAL frame, and that's an exact number. So you just have to make sure that your sampling period is this number is divisible by that, because then you can have a fixed number of samples per vertical blank, and you can just have this buffer. You can just fill it up, and you know that you fill it up in the same rate as the playback plays it, without having any audio interrupts. It's just the problem that this number it's a product of two primes, so this is the only values you can actually use, these 227 and 313 for the sampling period, which means that you cannot play anything higher than 16 kilohertz, which might not be enough for your needs. But you can actually observe that if you just take the number one higher, then you can use 124, which is the maximum sample frequency you can use. Then is 28 kilohertz. So you can utilize the maximum frequency you can actually use. And this is not entirely correct, but it's precise enough. It's like when your intro has been running for a minute, it's 1 millisecond off. So that doesn't matter. And of course, when you put this into a buffer, you have this cyclic buffer that just loops around, and you just make sure you put in the audio sort of well ahead of the replay, where the hardware is replaying it. And there's a slight trick here, that if you want, for instance, if you want to make some delay effects, some echo effects, it's usually you have some fixed length that you want to make the echo effect in. And if you make the buffer that same length, you can just sort of mix, instead of putting the data in, you can just mix the data in with the correct weights, and then you have an echo effect. It's very easy, instead of having to sort of pre-calculate this. Just a small trick. So that was about music, and just some general things that you tend to forget, turning out the auto filter and flushing the cache when you have written code. If you don't do that, you're screwed. Then I'll turn back to the code, because as I mentioned, one of the very important things is junket to planar conversion. And oops. So, as you might know, the basic operation in the junket to planar conversion is this merge operation, and you see it here. It's just these 7 instructions, and normally, what these merge operations, what it does is sort of swaps around some 16-bit blocks, and then swaps around some 8-bit blocks, 4-bit blocks, 2-bit blocks, and 1-bit blocks, and then it's done. And each of these blocks, when you have a normal junket to planar routine that you can find, then these blocks for swapping around in the different bit sizes, they're different because they do use different shift values, they use different masks and so on. But it doesn't compress very well when these pieces of code are different. So what you can use is you can use the same merge operations for all of these, and just have these shift values and masks and registers. And and use the sort of swap between the same registers, and then just exchange registers in between. So of course you have to know how chunky to planar conversion works in order to implement this, but there are some tutorials out there you can read about that. And then you can just update a few instructions to update the mask and shift values in between each of these mergers when you're going from 16 to 8 to 4 bits and so on. And this compresses much better because, I mean, it's more code than the original one. It's more instructions because you have these exchanges in between. And it's slightly slower, but not much. But it compresses much better because it's very self-similar code. So that's a trick for you making a very small chunky to planar routine in for 4K. I don't know if I have anything more. Well, I think that's basically what I wanted to talk about. So, unless there are any questions or code you would like to see more closely or anything. Yeah? So how much again by using the special instruction format? So it's very hard to compare because, of course, I can just compare the sizes of the code I write using the compact format and the normal format, and the difference there is quite big. It's like a factor of 1.5 or something. But it's not really fair because the code I write there will be very different from the code you would normally write, the compact code you will normally write, because of course you optimize the code from knowing what the sizes are of this in the special format. So I use all these huge floating point instructions all over the place. So it's not really fair, but yeah, something between 1.5 and a factor of 2 in that case. But I think it gets me. Yeah, I'm not sure. It allows. It makes it possible to use floating point operations all over the place without worrying about the size. That's sort of the most important thing of it, and it allows to have this utilize these register patterns. And the code for decompressing it is about 300 bytes. So I'm not sure how much exactly it buys, but it's. I'm quite sure it pays off. Oh, sorry, can you repeat? Yeah. Yeah. So the main thing there. So the problem is that the question is that all these various bit fields that have to be taken from one place to another when decompressing this. So how can this be done so compactly? And if you look closer at this figure, you see that all of the x's here and the x's here, they are in the same place. And the y's here and the y's here, there. You can't see when I'm pointing on the screen. But you see, if you look at the x's and look on the left and the right-hand sides, and many of the fields, they're actually in the same places. So for many of the instructions and all of these moving to and from memory and the floating point to and from memory, they have many of the same patterns in them. So you can reuse quite a lot of the code there. So what it does, it basically just plugs out these different bit fields that can be present in the instruction format, and then it switches on the first 4 bits, as you see, sort of specifies the instruction, and then does inserts most of the bit inserting is just ORing the bits in because they are usually in the right place to begin with. And that's, I mean, that's of course that's in the design of the instruction format, that it should be easy to translate. And one thing I did there was to place the register numbers in the places where they would be easiest to fetch. So I can actually show you the code here. Yeah. So here it starts. So the first piece of code, which is on the screen here, is reading in the instructions and taking out all these different bit fields, putting them into different registers so they are ready to be used. And then switching, having there's this jump table down here, switching on the first 4 bits. And then it just jumps into different places, which puts the bits in the right places. So that's it. It's not bigger than that. Okay. So, any more questions or? Okay. Thank you.